Yeah, hello. Hi, guys. Not sure, and I was waiting for Zubin to join, but he hasn't confirmed whether he was able to make it today. But I'll start in any case. So thanks for accommodating this class. Let me share my screen. Okay, first what I want to show you is too many windows here. Just bear with me. Okay. You all can hear me, correct? Okay. Yeah. Let me make the font a bit bigger, so you will see. Okay, so here is some stock taking, and what I plan to do for the rest of the remaining month or so. So this is the list, a summary of what we have covered so far. So we started with learning how to model systems as transition systems. Okay, in modeling, we saw various aspects of it, and how to model sequential code versus concurrent code, what a transition system is, and synchronous composition versus asynchronous composition, the state explosion problem, and how to encode a transition system as in propositional logic. And we saw how to use a SAT solver, although we didn't, at least as officially as part of this course, didn't go into the DPLL procedure, but we certainly spent significant time in studying how to use propositional logic to model actual problems, and as well as use a SAT solver to solve some of the constraint problems. So then we covered property specification, how to, logics to specify, to express property that we want to verify about our models or systems that are modeled as transition systems. We saw what labeled crypt key structures were, what exactly formally properties were, that is as sets of, they were defined as sets of infinite words over labeled crypt key structures. We saw the classification of safety versus liveness. And then we studied some popular temporal logics that are popularly used to specify properties for model checkers. We started with CTL star and its subsets LTL and CTL. We defined its formal semantics on paths and sets of states, compared that expressive power, saw some examples and so on. Then we defined what the model checking problem was in a formal sense as a satisfaction problem for temporal logic. Looked at fairness, what it was and why was it needed. We saw a formal definition of model checking with fairness. And we started looking at model checking procedures. We compared explicit state model checking versus symbolic model checking. Then we got into looking at CTL model checking in more detail. We looked at before doing that, we studied how model checking itself can be viewed as computation of fixed points. So model checking procedure, regardless of what kind of methods you used, can be situated, can be put in the framework of computing fixed points. So the theory behind fixed points, specifically Tarski-Kleene's theorem. And then we moved on to one way of implementing CTL model checkers using BDDs. So we looked at BDDs as compact representation for Boolean functions and operations over BDD, including the existential elimination operation, which was needed for doing computing images, which was the workhorse of the CTL model checking procedures. And we saw how to procedures for CTL model checking using BDDs with and without fairness, and how to generate counter examples, which you are working as part of an assignment. So then we started looking at inductive model checking, based on the notion of inductiveness of predicates, and to see if inductive invariance could be exploited to get faster convergence for model checking in computing the fixed points. We saw bounded model checking. Okay, that is something that I have not mentioned here. We started with bounded model checking as an incomplete method for showing existence of bounded counterexamples to safety and simple liveness properties. And then we looked at K-induction. Okay, so that's where we are. So here is the plan for the rest of the thing. So I'll spend today, talking about another inductive model method for inductive model checking method, which is based on the notion of, it uses the notion of interpolants. Okay, and interpolants is an interesting, can be used to generate inductive invariance or candidate inductive invariance. And then there is one other inductive model checking method that we will look at called property directed reachability. But before that, what I want to do is to do extend bounded model checking for arbitrary LTL properties. Okay, we have seen it for invariance, safety property, and simple liveness properties, but we will see a way to encode checking bounded model, how to generate bounded model checking formulas that can do bounded model checking of the entire LTL. And then there is another method for LTL model checking, which is a complete method, called the Tableau method, which is the standard method for doing LTL model checking. And that's another lecture is what. And then with the PDR lecture, that'll take about 4 lectures. And that'll leave us with 2 more lectures, which I want to spend, just keep it as slack. And then we want to do some revisions, and if you have just as revision lectures. Okay. So that's kind of a summary of where we are. So now I want to show you. Where is that? This one. So here is what I had proposed in the introductory, the first lecture to the course. Okay, this was the distribution that I had proposed based on the work schedule that we had. Now, in this, we already done assignment 1. The assignment 2 was not there, but I intended to get some written assignment on CTL. I never got to do that, but you're already working on the CTL model checker. Now, as I told you, there will be one other programming assignment, which I will kind of introduce today, which is not exactly implementing IC3 or predicate abstraction, because that I think I decided that it was a bit too complicated. This is something that where I want you to work in pairs. And you will be implementing bounded model checking. And what I will be discussing today, if it is possible, interpolant, and certainly the bounded model checking of LTL. Primarily, K-induction, bounded model checking, and probably some part of LTL model checking. Okay, so that is what, and then I want to have an exam, whether it will be 2 short quizzes or maybe just one quiz, and how exactly to conduct that quiz we can discuss. Now, given that assignment 2 has not gone out, so I want to distribute the 15% weightage that was allocated to assignment 2 between. I was thinking of splitting it 3 ways, okay? Because the CTL model checking, some of you expressed that it was harder work than what you had imagined as a simple assignment. So bump this up to 25%. So split this 15% into each of these things. 25%, give 30% for SAT solving and 30% for the exam. Okay, this exam will be what I'm planning is, and obviously it will be more to test if you've understood the concepts on these topics. Okay, there could be some simple questions, doing some examples to test you if you have understood the concept, and maybe doing some simple proofs by hand, combination of those things. What I was thinking was to give it out as like a take-home quiz. You will have half a day or maybe 3 hours or so, and then you just submit it on Moodle. Take 2 to 3 hours depending upon how lengthy the quiz will be, and then you will submit it. It will be, obviously, since I'm going to be proctoring over the internet, it will be kind of open book, open everything quiz, and that's what I'm thinking. Instead of having 2, I'll have one covering all the topics, okay, to be given in this week, on the week of 23 to 27, okay, maybe on the 26th or so, okay. So towards the end of that. So that is what I have planned, okay? So I'll put out a description of it. It will not be IC3 or predicate abstraction, which should have been kind of difficult, but you will be implementing bounded model checker, K-induction, and this bounded model checking, bounded model checking for LTL. Okay, so that's what you will be doing. But that will be you can pick a teammate for you to work with, and so you can discuss the problem and share the load. Okay, so that's what I'm proposing. So any questions or feedback? Well, so there's a saying in Tamil called Maunam Sammadam. So does Maunam mean Sammadam? Does silence mean you're okay with what I've proposed?
I was asking around what time, what day are you going to take the ANSEM?
Yeah, I couldn't hear you. Can you speak up,
Around what
please?
date
When is
are
this?
you planning on taking the ANSEM? Around what date? Like this month or December, or late this month, or
Yeah, so you're asking
yes, yes.
when do I plan to give the quiz? Okay. You look, I can do December 1st also. I don't know what exactly. There's no exam week or anything, is there? So
No,
this,
there's
huh?
everyone's taking. No, there is no exam week.
I mean, yeah, but I guess the term ends on 28th or something like that, isn't it? Then I don't mind giving it on December 1st. Okay.
Right. For SMT, we are doing the project.
What I was proposing was 26th, but if you'd rather have it on December 1st, I'm okay with that too.
Oh, okay.
If it's okay with everybody. So since everybody at home is at home, see when they were you were physically present on campus, there were restrictions, okay, that people used to go, were eager to go back home, for the break, and then so I had to, even if I wanted to postpone, that was not practical. But now that you guys are, home, and I think the grades are only due by December 15th or something like that. So I don't want to push it too much. So it's okay to have it on December 1st also, if indeed that you need some time. I mean, I can even use these classes if you want revision classes, and then doubts and so on, and maybe I'm too aggressive in predicting that I can cover this material in 3 lectures. But in any case, December 1st is okay with me, if it's okay with everyone. I know that not everyone is present here today. I think there are a couple of people missing. No, only one is missing. Shivang is missing. So I'll communicate with him. So most of you are here. So there are only 6 people in the course. So if it is okay for everyone and they'd rather have it on December 1st, I will do December 1st. Is that okay?
Yeah, I'm okay with it.
Okay. Yeah, so the weightage distribution, I'll modify this, will be same thing, 15% for assignment 1. This will go up to 25%, the model checker. This will go to 30%, and the quiz exam will go to 30%.
Also, can we ask questions about the assignment?
Yeah, let me, maybe okay. Yeah, speak again, because my,
Can we ask questions about the assignment, the model checker
yeah. See,
assignment?
I wanted Zubin to be here. So I'd asked him to actually, done the implementation so that he'll be aware of the thing. So you can, yes, I really would like, can you wait till tomorrow to ask the questions?
Can you also extend the deadline?
That I can do, since there are questions, I don't mind extending it till this Thursday, okay? So that you will have all your questions answered tomorrow, and you can submit. You have till Thursday to submit.
That's just 2 days.
Yeah.
It's okay.
Yes. Because I don't want to push it beyond that. So because you'll have to get started working on that, and I will also answer. See, I want tomorrow. I need Zubin's help to do that, to demonstrate some of the APIs for Z3, etc., which you will be using. Also, have you guys decided on your teammates yet? I mean, you can work on it on your own also if you don't want to work in pairs. So I guess not. You haven't thought about it?
Me and Kapil were planning to team up.
Who's this?
Argadeep.
Argadeep.
Yes, so me and Shomudev are planning to team up.
Oh, okay. So that leaves that by elimination means that Rishikesh, you will have to team up with Shivanga. I mean, have you communicated? Rishikesh is here. I mean, Shivang, I haven't seen. He's not, doesn't show up to the Zoom meetings regularly. So Rishikesh, you are stuck with Shivang. Is that okay with you?
Yeah.
Have you communicated with him at all?
Yeah, like he's my roommate, like back in
He's your roommate. Oh, he, in the sense?
CMI.
He used to be your roommate, you mean?
Yeah.
Ah, okay. So you know him. That's good. Yeah. I'll put out a description, detailed description of the thing. So hold on to your questions till tomorrow, guys. Rather have it, thoroughly discussed with him. Having Zubin also implemented, he has first-hand impression of what might be some of the technical issues, okay, with respect to the BDD packaging and so on. Yeah. No, this is not what I want. It's my old slides. Yeah, there was some small loose ends that I want to tie with respect to K induction before I move to interpolants. So here is an example. You want me to make it bigger, or this is okay? I think anything bigger. Yeah, okay, this may be bigger. Still good. So here's just an example. This is kind of my favorite example, which rotates the values in, continuously rotates the values contained in 3 variables, A, B, and C. There's also variable X, a useless variable, which is never modified by the program. And N can be some arbitrary number, arbitrary large, and I just put star there to say that it can be anything. So I keep until up to N, I just keep rotating the values until I hit N, and then I get up. So what I want to show when I get out is that X is 0 and A is not equal to B. Okay. So if you were to be using traditional model checking, how would you do it? I mean, you've already done something similar in assignment 1. So you can define a transition system T that models this entire program, including the while, okay? And you know how to do that. We have discussed that in class, okay? And then you can model check using fixed point method. With the CTL properties, okay, so the way that we have done sequential model checking is how not only the state, we have usually made it contain not only the variables, but also a PC. Because if you want to model all the control flow, etc., you know that we had to do PC, have to model PC. And then your property would be that whenever I'm here at location 7, x must be equal to 0, and a should not be equal to b. Okay. First of all, you're convinced that it is when you get out of the loop, x is equal to 0, correct? Because x is never modified, and a is not equal to b. Okay, because it's just rotating, and therefore, when you get out, a must be not equal to b. So how many how many iterations would traditional model checking, the fixed point computation in this case, take to converge? No answer? So if you had the transition system model the while loop also, in order to get to this location, you will have to completely unwind the loop, right? Because I is increasing only one at a one number at a time. It's being incremented once. Therefore, since we are doing it, you never get to this location unless you iterate over this as many times as n. And if n is very large, this will take a very long time to think, because the state, when you model it like this and include I, n, etc. in as part of the state, the fixed point getting to a fixed point I and n will keep on changing as long as you're executing the loop. And since the way we model is, once we reach, for terminating programs, the assumption was that it'll iterate. It'll self loop in the terminal states. And therefore, that's why I'm saying, since you will be modeling I and including I and n as part of your state, since I keeps changing, the fixed point is only reached, can never be reached until you completely iterate over the loop. Therefore, for these kinds of programs, okay, sometimes the traditional model checking can end up taking a lot of time. Is that do you understand that? Is that convincing as to why this requires you to pretty much unwind the loop before you reach fixed point convergence?
So to even represent this as a finite state system, we will have to specify some bounds for I and n.
No,
Right?
I'm saying even if you specify bounds for n, suppose my bound n is 1,000,000. What I'm saying is it'll take as many as n, okay?
Right. Yeah.
So I'm assuming when I put star, I don't mean it's arbitrary, although I did say that. I mean some finite number, say that I don't care. I mean that's what I mean. So even if you put some n, yes, for smaller n's, for it'll you'll luck out. So what I'm saying is that it is dependent on certain things. Values of certain variables that your property is not even dependent on. So you can do better on these kinds of things. And that is when things, inductive model checking will become, will do much better. This is a classic example where for K induction, or in general inductive methods. So let's see, if I were to be doing K induction, what I'll be doing is kind of doing induction on the, so T, yeah. So here's what. So I mean, this is I'm expressing it in a stylized way to be suitable for software, but pretty much that's what you're doing. You don't, yeah. So you will, yes. So the base case will be, you will have to check if your initial condition, what is the property here? The property that you want to prove is x is equal to 0 in A and B. Okay, let's suppose that is the invariant property that I want to prove. Okay. So now I can pretty much only look at the body. I'll have a transition relation for the body, and I will prove these three things. Okay, so whether from initial state, the initial state is included in the property. Okay, that's what this proves. My initial state is x is equal to 0, y is equal to 0, and n, say star is some fixed value, a large value. And then I'm initializing A to 1, B to 2, C to 3. Then I will see from that initial condition, if that initial state is in P. Okay, from the initial state implies P. In the inductive step, I'll have to do this. Okay, so obviously this property A not equal to B. Okay, firstly, is x is equal to 0 inductive for this? See, x is equal to 0 is inductive, but nonetheless, this is what setting up of K induction means. So what I will do is, I will assume that my property holds good. If I started from an arbitrary state in which the property held good, and then I will do that T, I will do the transition system once, which means by assuming I is less than n, and then I execute the body once, and then if I was not less than n, is x is equal to 0 and I not equal to B hold good. This fails, right? Because since x is never changed, x is equal to 0 is true, but A, since I'm starting from an arbitrary state in which the property holds, which is A not equal to B. So from A not equal to B, if I rotate it once, I can't be guaranteed that A is not equal to B is preserved. Okay, so this is that would be true if A not equal to B was one inductive, but A not equal to B is not one inductive, because when you start from an arbitrary state, A not equal to B, you don't know anything about C here, okay? So you know that A is not equal to B, but C could be, might as well be equal to A or C, and therefore this fails, okay? Although x is equal to 0 succeeds because that is already inductive, one inductive, okay? Because x has never changed, and therefore if you assume x is equal to 0, x is equal to 0 is one inductive on its own, okay? If you start from something, from an arbitrary state, not the exact initial state, okay? So that's what inductive methods do, okay? So if I start with an arbitrary state in which the property holds, after one, if the property holds, then you can assume that that's what K inductive means. Therefore, so here x is equal to 0 holds, but A not equal to B does not hold, okay? So because it is too inductive in this case. So that's why, so now, if you now do this check, that you start with a state in which P holds, which is x is equal to 0, A not equal to B. You go in, do the body once, And then you assume that, say, if you were to be in a state in which P holds a gain, okay, which is A not equal to B, and then you do that again, then does A not equal to B succeed? See, here it succeeds. Why? Because you are assuming that after executing T the body once, you would have moved B to A and C to B and C to A, and therefore, so it is kind of eliminating those states. So now if you assume A is equal to B, then that can happen only when if you started out with A not equal to B not equal to C, and A, B, and C are all distinct, and therefore this will succeed. Okay, and that's what because A not equal to B is K inductive. So after two iterations, you have at least with respect to this property A not equal to B, you would have succeeded, and therefore you can actually conclude that P is true for arbitrary number of iterations. So regardless of how many times you iterate, since you know that after two iterations, with respect to the property, it is has reached the fixed point, you will end up proving it. And this is what is happening in K induction. So here the property happens to be too inductive. By too inductive here in the case of while loops, what it means is if you assume that the property hold good, it held good for after each iteration twice, and then if it continued to hold, and in this case it happened to be with that was strong enough to prove that after three iteration onwards, A would be that this would that this would hold. Is that help you, this example? Is that clear? Is that kind of, does it, I mean, you at least understand why after, if I assume P, and then I look at only those states after one iteration, P is true again, that after two iterations, the property A not equal to B will become true. What happens after, I guess you're not convinced, okay? So if A is not equal to B here, so B went into A, C went into B, and A went into C. If C was equal to, obviously A not equal to B may not hold good there, because C, the starting C might have been equal to equal to B, okay? So if that were the case, then A will not be equal to B after one iteration. But if you start with P and then you assume that, oh, after that, suppose I include only those in which A is not equal to B, then that can happen only if A not equal to B not equal to C was continuously holding good as an inductive invariant in the at the beginning of the loop. That's why what this is equivalent to is, another way of proving this property is to say that if A not equal to B not equal to C, if all three were distinct at this point, that will continue. See, if you start from a state where A not equal to B not equal to C, after you do this, you will this A not equal to B not equal to C is always preserved by this loop, okay? So it is inductive. This property is inductive regardless of what your initial state is. And that's why that is what is the crux, what's happening, okay? This is the inductive A not equal to B not equal to C is inductive with respect to the body of the loop, because if you assume it holds good at the beginning of the loop, then after every iteration it continues to it'll hold, okay? But A not equal to B not equal to C is not one inductive, okay? So that is what is not a one inductive invariant. That's why this, you needed a stronger, this is one way. You could come up with these kinds of inductive predicates that are not inductive invariants, okay? And that is the case. That is another way to prove it. But K-induction allows you to, in some cases, to end up discovering such inductive thing. Okay, so for this property, this is an inductive invariant that you need to guess. Okay, if you could guess this, then you could. This is inductive, okay? But A not equal to B is not inductive, and that's why you are not able to show this. Therefore, the method is, if you want to, prove this in, smaller number of iterations, either you have to discover such strong inductive invariance. So this is the case where the property is not inductive, but there exists an inductive invariant property, okay, which is A not equal to B not equal to C. What K-induction does is, it, by doing this kind of inductiveness check, one inductive, two inductiveness check, sometimes, so in this case, regardless of how many times this loop might take to exit, you'll be able to show that this property, if it is too inductive, after two iterations, you are able to show it. Okay, so that is what is happening. Okay, I thought I'd take an example from software and then do it. I hope this. I don't know if it, based on the response, I don't know if it enlightened you or confused you more, okay? So I hope it was similar. So this is a case where it is too inductive. This property is A not equal to B is too inductive because, although it is not one inductive, okay? And A not equal to B not equal to C is an inductive invariant, one inductive invariant, and that's what you get. The existence of that is what is checked by this two inductiveness checking. So that is the idea. Okay. Yeah. Okay. Okay, what else did I want to? Let me go into full screen, whether there was anything that was left here. Yeah, I think I will. Yeah, there were two things. One is there's this, yes, the correctness of K-induction is dependent on two things. The soundness is saying that if this is K-inductive, there always exists an inductive invariant. And that's what I was showing there. I showed a way to set that thing up for that code example how to show that property that it was two inductive. X is equal to 0 in itself was one inductive, but A not equal to B was two inductive. And I also showed you what the corresponding P star was. So in that case, A not equal to B not equal to C, that was stronger than A not equal to B. That was the two inductive property. Now, in general, how do you prove this existence? Now, that is what I've shown here. That has to be an inductive thing here. So I've shown the base case, and you can do the thing. So if P is not one inductive, and suppose but P is two inductive, then here is something, you know, I've shown how you could derive a predicate by using existential quantification elimination. And here I've defined a P1 star, which is, I've derived a P1 star from P by eliminating those things that take you out of P in one step. And that's what this thing is doing, okay? So here, if P is one inductive, this is not true, okay? Because if you assume P and then you march ahead by one, it is not the case. There are some states, P states, which take you out of it. And that's why this will be false, which means that this formula, which is the negation of this, is satisfiable. And what I'm doing there, I'm defining P1 star as something which you get by taking out from P those states that take you out of P. Okay, and this is exactly what you know how to express that in terms of existential quantification. And through some existential quantification jugglery, what I've done is I have converted that into a universal quantification. Now we have to show that this is two inductive. That you can do. So if P is two inductive, then this is the formula that'll be true. From this, you can actually show that P1 star is one inductive, and that is the proof I have. You know, I have here. This is very, very simple. I mean, all you have to do is to kind of stare at it for some time, and then this is just moving quantifiers, and you will get it. And I will let you do at your leisure. Now, this argument you can apply for any after any k steps, okay, through a sequence of existential quantification elimination. That's what you get by doing it, and that shows that this k inductiveness check is sufficient to guarantees the existence of a one inductive property. Okay, and that is what I think. So that's being used. Okay, so and the other property, the completeness for safety, states that if P is invariant for M, but it is not one inductive, there exists a K such that P is K inductive, okay? Now that you can show, I mean, I've shown pictorially here, okay? Now, the existence of a P is guaranteed because what are you doing here? You are kind of, taking out, not, this, because this P itself has several states that in one or more steps lead you to a not P states. And therefore, so eventually all these states that are bad states, counterexample to induction, will take you to a state in which they may be P, but they will take you in one or more steps into a not P states. That is, all these states are such that eventually not P holds from that state. There exist paths from which not P holds. Okay, so what you're doing is it's a counter example to a eventuality property. And as we saw, the reoccurrence diameter is a bound. for such eventuality, simple liveness property, and that's exactly what the value of that k is. So there is a k because the counterexample to eventually not p holds good from some of the states in here will be, at most it can be the reoccurrence diameter, between that before it loops back like, like this, and that is the bound on this, and therefore k, indeed, the k bound for k induction is the reoccurrence diameter, okay? That is the longest path from a p state that takes you to a not p state before it lassos, okay? And that is the, and since that is every lasso of that kind, there is a bound on that, which is the reoccurrence diameter, that guarantees the existence of k. So that is the argument that you'll have to make for doing that. Okay. With those two, those are the two things that I wanted to check. So any questions here? Okay. So let me now move to, what is it that I want? Forget the name of, what is the name, man? Ah, it's right here. Okay. Okay, so now I'm first going to start by introducing this notion of interpolant. Okay, this is a very, very old notion. Okay, so this was introduced by Alan Craig in mid 40s something as and I'll first give you a definition, okay, and then see why is it relevant, for us. Okay, this is a purely logical notion. Okay, so given two formulas A and B, pay attention, please. So if A and B is false, that is A and B are inconsistent with each other, an interpolant, okay, for A and B, the pair of formulas, is a formula, I'm sorry, read this as A prime, not A question mark, A prime, if A implies A prime, and A prime and B is still unsatisfiable. That is, A prime and B is still false. Okay, A implies A prime means A prime is weaker than A. Okay, but it still is inconsistent with B. And there's an additional syntactic restriction that A prime refers only to the common variables of A and B. Then such an A prime is said to be an interpolant of A and B. It is in a sense, see, when you have A and B, so what is the intuition? So A and B is unsat. Okay, false means it's unsat. It gives you, this can give you an explanation of how far you could weaken A and still have it be inconsistent with B. That's what this thing is saying. So in some sense, it's saying, oh, there is a reason why A and B is false, but can I, kind of, yeah. So how far can I still, do it? So in a sense, it will give you an explanation of why A and B is false. Now, I'll show you an example which is somewhat is relevant in the context that we are, in the context of model checking. Let's suppose A is this formula. What does A represent here? I is an initial state, T is a transition relation. So what does IS and TSS prime denote? Please, someone should be able to answer that. I just want to make sure that you guys are still alive.
So S prime is some state reachable from L.
Yeah, the pair of states, yes, it's all S prime should be reachable from S in one step, correct? Those are the things that it satisfies. And P is, say, a property, and which we want. It's a bad P, not P is a bad state, okay? So an interpolant is then an A prime such that is something that includes all the one-step image under I, but still A prime, it should include all one-step image, but it still does not intersect with a bad state, okay? Yeah, I'm sorry. Yeah, so there's a parenthesis missing here. So this parenthesis should close here. So that's what this thing is saying. So you see, see how far I can relax and yet still not reach the bad state. Okay, I mean I'm using it in the context of image for you to do it. Okay, so that's the significance. Okay, so in logic, this is actually used to somehow explain as one of the explanation for an unsatisfiability proof. Oh, sorry. So all question mark, you read it as S prime, okay? So there is some thing. So pretty much, yeah, so that's because you see, what is an interpolant is an A prime. See, IS and TSS prime can also be written like this. See, because additionally, what the interpolant says is, it should only include, S question mark is S prime, read it as S prime, please. And it additionally says, that's the reason for the restriction. A prime of S prime, that should only include things that are common between these two things, okay? So it should only include S prime. So if A prime is restricted to include S prime, then it is exactly this one, okay? It means, and still you want this A prime, S prime to contain all this, then it pretty much means, because S prime does not contain any of these variable S, this is exactly what it means. So there exists in S, so that IS and TSS prime is exactly the one-step image, okay? That implies A prime S prime, and it still does not contain any bad state, okay? So in other words, this is an over approximation. The interpolant is an over approximation in the sense it not of the exact one-step image. What is an over approximation? It includes all one-step image and some more additional states, okay, that are not reachable from IS. But the over approximation is such that none of the states, unreachable state that it includes, intersects with not of P, okay? And that's what is happening here. So A prime is the interpolant. Here I is the initial state. A is the exact one-step image, that contains all the states that you get by mapping the states in I in one step, okay? That is the one-step image, okay? Note that the one-step image may not completely contain I. It may contain some states that are in I, but may not. So A prime is this. It's an over approximation because this implies A prime S prime. Still, it does not intersect with not P, okay? So that's in a way it is telling you. So if A was not intersecting with not P, that's what, the unstep image, how far can I loosen it and still not hit any of the not P state? Okay, so this is what it is. Indicating. So now these interpolants, you can, of course, these interpolants are not unique. Okay, there can be several interpolants for a pair of AB, and there are ways, just like resolution. One can automatically show contradiction in propositional logic, and you can extract unsat core. Interpolants can also be extracted automatically from resolution proofs. We won't get into that, but we only, and there are provers, even Z3 has support for extracting unsat core and interpolants as well. Okay, so this method is one where it tries to exploit an interpolant for deriving inductive invariants or candidates for inductive invariants. How is what I'll explain. Now, yeah, so before I move on to doing, so is the notion of interpolant clear? Please ask questions if you still have doubts.
So one comment.
Yes.
So interpolant is basically acting as a separator for the two formulas A and B, right?
Correct. Yeah, but it is, yes, interpolant is acting as a separator, but yes, a loser separator. I mean, the A and B are already separate, okay?
Yeah, otherwise there won't be an interpolant.
Yeah, so it is saying, hey, how far can I even loosen up the A and still maintain, okay, that separation?
Yeah, yeah.
So A is automatically an interpolant, okay? That's the strongest interpolant, but that's useless, okay? So you would normally want to have weaker things, okay? Some loosened things so that you can, and that's what you'll see, you'll exploit in doing it. So yeah, so this is what I said. A prime interpolant, you're right, okay? It's a separator, but the key thing is it asks the question how far I can loosen A. Okay, that's a word. So that's why it's the over approximation is important. So good interpolants are usually weak, weak interpolants. They must be much weaker than the A itself for it to be useful. So it's an over approximation. One way you can over approximate the image under T and yet make sure that it is not violating the property P. Okay, so this is first, Alan Craig showed existence of interpolants for first order formulas with some interpolated entities. It is always going to be quantifier free. If A and B are quantifier free, it can be extracted automatically from a refutation proof, from an unsat proof. And propositional logic, it is very much similar to unsat core extraction. And some people have extended this for other theories beyond propositional logic. And there are several good theorem provers that do extract these interpolants. So that is just, we're going to treat this as a black box, pretty much like what SAT solvers, the way we are treating SAT solvers. Okay, now, how is it relevant in the context of bounded model checking? So that's what so here is event. So B is, if you see this, B is now a K long bounded model checking formula. I mean, the whole thing, A and B, that I've split the bounded model checking formula, K long. A bounded model, when I say bounded model checking formula, it is the formula that whose unsatisfiability guarantees you, or whose satisfiability shows you the existence of a violation to the safety property P of length less than or equal to K, okay? That's what I keep saying as BMCK, okay? So if I split BMCK into two parts, A and B, the A part is just the 1 step from the initial state. The rest is from the remaining k. So this whole thing is k plus 1. And so if I split like this, and the only thing common set of variables between A and B are S1, okay, which represents the what you get, the state that you get after one step. And an interpolant between these two formulas. Now here I'm extending B, okay? B there, I only, in the last slide, I showed it as including only a bad state, not P. But here, I'm including this entire part from 1 to K. Now, if I get an interpolant of these two things, and say I call it K-safe interpolant, so what does that, an interpolant between these two formulas, denote? It denotes it is an A prime that contains only S1, because that's the only thing common between these two things, such that A prime of S prime. So the one-step image is contained in that, in A prime of S prime. And A prime of S prime is still the conjunction of A prime of S1 and B is still false, okay? It still is separate from B, okay? That is A prime of S1 implies not B. And so this means that from A prime of S prime, so this is just rearranging these things, it shows that any state from A prime, which is an over approximation in one-step image, is still safe, okay? K steps safe. Up to K steps, you won't be reaching a property that violates, a state that violates P, okay? That's what it guarantees, the interpolant, okay? So it separates A prime is such that any of the states that is included there, not in the image, not in the exact one-step image, is still is separated from not P, at least up to K steps. That's what it guarantees. Therefore, yeah, so the A prime of S1, the interpolant, that's why I call it K-safe, okay? The sense that it is safe up to K steps, okay? So this picture is what tells you what that interpolant, the property guarantees you. So it is an over approximation of one-step image, but the B that I'm using here is longer. It's a K-step reachability to a bad state in one or more, up to K steps. So this is what it's saying. So it may have more states that are not reachable in one step, but none of those states is reaches not P in K. Okay, that's why I call it K-safe. Okay? So you see where we are headed. So therefore, you could use, if indeed in the process of bounded model checking, the bounded model checking keeps checking these kinds of things. Okay, if I end up reaching a bad state in K steps, but if I know if that is unsatisfiable, if it's satisfiable, then of course it's an error. You're done. If it is unsatisfiable, you keep on just increasing K in bounded model checking. But here, what the idea is, by the way, this idea for using this BMC was due to Ken McMillan. Okay, so and he built a thing. Ken McMillan used to be at Cadence, and now he works for Microsoft Research. So he put this thing to use. So the idea is, if somehow we can use this over approximation, which gives you from the unsat proof that there are no K-long counterexamples, can I now use that to somehow speeden the convergence, or at least use it as a candidate for searching for inductive invariance. Okay, so how is that done? So this part you understand, correct? So by just changing B to be a path, not just the property, a path leading to not P in one of those states, now I'm able to, and if there is a good interpolant, for this, which is, we can have, now I have know that this, I can kind of use this as the over approximation instead of, to put it to good, good use. Yeah. Any questions here? Okay. Yeah, so K-safe interpolant A prime is an over approximation of one-step image I, so that none of the states in A prime can lead to a not P, that a bad state within K steps. So that is the question. Okay. What if? So here is how it can. What if after you compute a K-safe interpolant A prime, if that itself is within I? So if they say the situation is like this. So you have a exact one-step image. You compute the K-step A prime. So not P I'm denoting here, by the way. All the rest of it is P, which means I satisfies P and all these satisfies P. So A prime, what am I saying? Yeah, so I is here. If A prime itself is included in I, then I has to be inductive, correct? Because A prime, in case of, we'll never go, it is inside I, and therefore, so if A prime itself is included in I, then it means that, it is already in there, and therefore you cannot, because as you know, this is inconsistent, okay, with B, and A was inconsistent with B, and therefore you can't even get out of, I. Therefore, I then, if that interpolant itself is included in I, that it must be an inductive invariant, because everything will, it's a fixed point, okay? It'll go only inside I, it can never go outside, outside of that thing, because in K step, you're guaranteed that you are, you've reached a fixed point. Okay. Therefore, if you are able to, if you've done an unsat up to something you got unsat, then you can do it. And this can now be more generally. Suppose AK1 is a K1 safe interpolant of I. But suppose AK1 is not contained in I. That is, I is not inductive. Then if AK2 is, if I compute from, if I now, take the union of the original I and then the AK1, and then compute a K2 safe interpolant, okay? Or even, for some K2 of I union AK1. That is pretty much what I'm making is, I'm enlarging the original initial state to include everything that is included, to include everything in AK1, because I know that it is K1 safe. And then I, once again, compute, this K2 can be K1 itself. So then, if that is contained in I union AK1, then that is an inductive invariant that can prove P. Okay, so which means that I'm now done. K1 it is not folding back, but K1 plus K2 it might be folding back. Okay, so I can repeat that that interpolant. I can do iterative interpolant computation over K-long BMC formulas from the over approximated initial state, and that's what I'm doing here. Okay, so here this is I, And so AK1 was not contained in I. So this is I, and this small horizontal thing is A. That's the exact one-step image. What I have shown here in crossed boundaries is AK2, and there is a bump here for AK2. AK1 is not contained in I, but AK2 is contained in I1 union AK1. And AK2 is the K2 step interpolant of I union AK1. That happens to be contained, which means that I union AK1 is an inductive invariant, and that since it is still included in P, that is inductive invariant that can satisfy. Inductive invariant that can prove the property. So the idea here is you run BMC up to some K. Okay. After that, if you're still sure that it is the system is safe after K steps, now you compute the interpolant and see if the interpolant can be used then to check, it can be a candidate invariant, especially if it is contained in the initial state. If not, you do that interpolant computation iteratively before you bump up your K. Okay, so in that sense, you are putting the unsatisfiability check of K step into better use to search for inductive invariance that might end up, rather than in K induction you kept on increasing your inductiveness check continuously was increasing, whereas here you need to only, you can restrict yourself to doing K long thing if you use this acceleration. Okay, you do the over approximation of the image. Okay, so that's, yeah, is this clear? Any questions here? So when I do this, what AK2 is, it ensures that it is safe. If I start from I union AK1, which AK1 is already K1 step safe, then I fold into it. So it is inductive, and it is, so in K2 step, K1 plus K2 step, I've reached an inductive invariant. Now you can choose these K1 and K2 however big or however small that you want. But whatever you do, so after you're doing K, you can, the rest of the thing you can keep on, only it's K long formula. Yeah.
K2 is a K2 safe interpolant of I union AK1, right?
Correct.
Then how AK2 is a subset of I union AK1?
No, but it is I union AK. No. You see, interpolant. So maybe I made a mistake. Okay, so let's see. No, that, I'm sorry. I think I union. No. It is contained in I union AK1.
But an interpolant is a superset.
Yeah, it is. It has to be a superset only of. Let's see. So it has to be an over approximation of the one-step image. That's all. Okay. It has to be what I have not shown here is one-step image of I union AK1. I have not shown. Okay. I mean, what is missing here is, don't confuse the I union AK1. Yes, it is contained in I union AK1, but AK2 has to be an over approximation of only the exact one step image of I union AK1, which I have not shown here, which I, to be true, I should have shown it here. Okay, that may not be in that, but it is here. AK2 happens to be an just like here. A prime is an over approximation of A2, but I happens to include that. Yeah. Okay.
Okay, I was confused. Got it.
Yeah. So, but that's a good point. Yeah, I mean, that's a good observation. Yes, I should have, to be clear, I should have shown probably the one-step image of I union AK1, which I have not shown here. Yeah. Yeah. Correct. But that's a good observation. Yes. So this is just showing I can use it for, however, thing. And that's what this procedure is doing. Okay. So I will just quickly go through this and I'll stop. Okay. So I can even see pretty much. Okay. Since what you do here is the first part, the while, yeah, there is a big loop. This part from here. Okay, this is actually, this is in the book, by the way. And I've only added some illustrations, etc. To make it, I think that's my contribution. So let me see what happens here. So the first part is the regular bounded model checking part. So Q is the initial state, you make K is equal to 1. And when you go into this while loop, the if part, the then part is regular model checking. See, so what you do here is you take K-long thing, okay? The K-long BMC formula, then you see if it is SAT, which means if there is a K-long counterexample, K plus 1 long counterexample. If so, if you found a counterexample, you return false. Otherwise, you can increase K. See here, I'm not saying how much you increase because I'm using this. Okay, there is a check for if Q is equal to S naught. Okay, because you will see why, because I'm taking the union of the interpolant in the else part. Okay, so here if Q is equal to S naught, that is I'm in the beginning, then I will declare it as a real error. Otherwise, I increase K. Now that K could be however big or however small that you want, and I will just then initialize S naught. But before I start checking doing the BMC check, there is an else part. Okay, that is if it is unsat. If I have not found an error, that means if I have not found any bug up to K long, then what I will do is now I compute the interpolant of whatever the initial state at that stage is between A and B, and then do this check. If the interpolant is a subset of the current Q, then if it is, then I know that I have reached an inductive invariant. Then I will declare that it is verified. Okay. If not, then I will add that. Okay. If that is not contained, I know that it is not. I have not reached the fixed point, so I will add it. Okay. I will add the interpolant. I will union the interpolant with the current initial state to do more. Okay. The interpolant. I mean, I can keep on extending until I use that to see if I can do certain number of up to interpolants. Okay, so this is the interpolant part. Okay, so then I will go there. So if in the next stage, if I find an error, after I have enlarged my initial state, if I go back and then do the check, you see then a bug that it finds is no longer a true bug. That's why you cannot conclude anything. So you will have to come here, and that part is only used for computing a series of interpolants to see if you reach up to if you converge. Okay. So now, if you're not getting good interpolants, then you can go back. Okay, and increase your K. Make it larger than that K that you have, and then you can start from the from the beginning if you wish. Okay, so basically after you get an unsat proof for a k-long counter example, that is, then for some k you can now check if you think using interpolants that you've reached some inductive invariant by iterating over the approximated the interpolant in initial state to see if you reach convergence. If you're not getting good interpolants, then then you can go back and increase the original k. Okay, and so on. So that's what it is. So you really do this interpolant iteration after you hit a certain k, beyond which either you're not able to go or you think it is large enough. I will give it a try. Okay, kind of a thing. Yeah. So if if you can't find, obviously if it is unsafe and it is for longer k, then you will have to come back and then bump this this k. Okay. That's what you have to do. So the advantages of this one over k induction is significantly it is this one, second one, because every time you're only doing the BMCK for inductiveness check on k long, okay? Whereas in k induction, that was getting longer and longer and longer and longer. Whereas here, with the help of interpolants, you're keeping the length of the inductiveness check to a fixed k, okay? And this is forward, okay? It is not working backwards, and therefore, in the worst case, the convergence depth could be the diameter of the diameter of the transition, whereas there it was reoccurrence diameter. Okay, so that is the that's the idea. Yeah. So do I have any? Well, I have an example, but that is it's too late for us to discuss this today, and I will end here. Okay. Any questions? Any questions regarding anything? Okay. What I proposed, final exam, weightage, anything. Oh, you can think about it. You can come back tomorrow. And tomorrow, hopefully, I will come back with any questions you have about the assignment, and we'll be ready to take. Okay. I'll see you.